Welcome to Chemistry 111. Today we'll be starting a new chapter, Chapter 9. But before that, we definitely want to do a little bit of review because as we're moving forward, we're going to get into the math portion of this class. And of course, if you have to take Chemistry 2 at all, it will be a lot more math from there on. But the book method I'm going by, there are several different ways of naming this, but right now the book is called Atoms First. So we treat how do we look at individual atoms before we get things like the chemical reactions and whatnot, which is why we went to light and electrons and Vesper models. Some of the traditional ways it's taught are also the taught in where we teach the math, and then we jump into atoms and whatnot. So depending on how you treat it, we're saving the math to a little bit later. But so the test, remember, Thursday, you can take it early. Come find me. I'm going to be here till 3 today. You should be able to find me. Reminder, you're allowed to have 1 page of essentially notes. You can make your own notes. It just has to be handwritten. I don't want you just to photocopy like a chart or table. So like if you need, say, a reminder of the different shapes, different like electron geometries and molecular geometries, you can include that on there. If you want to include any example problems, like the definition of oxidation and reduction, that'd be something you can include. Just 1 page, front and back, something to help reassure you, since we're not doing a take-home test. So, but quick reminder, you will have the Pauling electronegativity chart given with you along with a periodic table. The Pauling electronegativity is that chart with essentially those numbers, so you can figure out if the bond's polar or not. You'll also include a solubility chart. It's going to be a full-page solubility chart, so hopefully it's not going to be too blurry that you can't read it. Over. Remember, on S is I think S is soluble, I is insoluble, and D is decomposed. You can hopefully use that chart within reason. Now, as I said, before we get into the chapter, I'm going to do a little bit of review to remind us what mathematical terms, what mathematical concept learned are. Okay, with that in mind, so we've learned a few simple things. Obviously we know density, but density isn't the big thing. The one big thing we've learned is molar mass. So molar mass is defined as the mass, the grams per mole. We calculate that number by looking up on the periodic table the atomic mass, essentially the average atomic mass, the weighted atomic mass of each compound. For example, carbon is 12. If you want to get really specific, maybe 12.01 for carbon. Hydrogen is something like 1.008, I'd like to say. So if I was doing the molar mass of methane, which is CH4, it would be 12.01 plus 1.008 times 4. But for all intents and purposes, we're going to say, 16. If I wanted to do, say, sodium chloride, sodium is approximately 23. Chlorine is approximately 35.45. Adding them together, sodium chloride would be 58.45 grams per mole. Now, how did we use that? We use that to calculate the moles. Remember, a mole is a convenient an amount of something, just like we would say a dozen eggs or gross of paper. We use moles to measure atoms in a way we could figure out. So if I had 25 grams of sodium chloride, we could calculate the moles by simply using the railroad tracks method to say, okay, if I want moles, I have to get 58.45 grams per 1 mole. And then when I do this, the grams of sodium chloride cancel with the grams of sodium chloride to give me moles of sodium chloride. And so we'd say, oh, 25 divided by 58, and how many moles did I have? I would have 0.427. If I wanted to keep sig figs, 0.43 moles of sodium chloride. Now, the other thing we learned about, which will not come up nearly as much, was Avogadro's number. Avogadro's number was 6.022 times 10 to the 23rd, and that was atoms or molecules per 1 mole. And we use that to figure out how many atoms of this we might have had. How many molecules did we possibly have? And we looked at mole ratios. Like, for example, you could calculate, well, sodium for every 1 mole of sodium, you would have 1 mole of chloride. And methane, for every 1 carbon, you would have 4 moles of hydrogen. And we did things like percent by mass. But the main thing that will come back to us, and we need to make sure we know how to do, is how to calculate moles from molar mass and turn moles into grams. So if I had one last practice, if I had 1.85 moles, I'm only using mass, we've already calculated the molar mass, what weight would that be? Well, based on our molar mass, would set up for every 1 mole of 16 grams. So you'd have 1.85 times 16. So to get grams, we multiply moles by molar mass. To get moles, we take grams divided by moles. As I said, when we get to stoichiometry, which is the title of this chapter, we need to be able to convert grams to moles, moles to grams. I realize it's been a while. It's been like a test and a half. So we've had to really do this, which is why I felt we need to spend just at least a half minute covering that before we go on to this. Okay. So this is where we're actually going to really, really start to use this. And this is stoichiometry. Too far. So now, last chapter, we just started to introduce the idea of balancing chemical equations, where we're going to put the coefficients in front of the compounds in order to make the number of each type of element on each side equal. But so the reason behind that is so when we calculate this, we can figure out how much product is formed, how much reactant is consumed. We can essentially diagram out a reaction and know what all is going on. This balanced chemical equation will serve as a map to guide us through what's called the stoichiometry, the calculation of. So if I say 2 potassium chlorate goes to 2 potassium chloride and 3 oxygen. Besides being a decomposition reaction, besides being a redox reaction, where chlorine goes from positive, I'd say 5 to -1, and oxygen goes from -2 to 0. Besides those situations, the stoichiometry tells us for every 2 molecules of potassium chlorate, you would form 2 molecules of potassium chloride, and you would form 3 molecules of oxygen. It's telling us essentially what's happening on an atomic scale. You could scale it up and look at it on a molecular scale. I mean, on the scale of moles, that instead of 2 molecules, we could also look at it as 2 moles. Like if I say I need 2 eggs to make breakfast for 1 person, you could also say, well, I need 2 dozen eggs to make breakfast for 12 people. I'm scaling it up. That way every person gets 2 eggs. So we can scale this up to say 2 moles of potassium forms 2 moles of potassium chloride and 3 moles of oxygen. And we can even scale it up so it's not so nice. If I had 30 moles of potassium chlorate, these coefficients tells me I would form 30 moles of potassium chloride and 45 moles of oxygen, because it's a 2 to 3 ratio. It's a 2 to 2 to 3 ratio, and it doesn't matter what I'm looking at. From moles or from molecules, I can compare all things. Now, the first thing we will need to do is convert moles of one substance to moles of another using a mole-to-mole conversion. We're going to use dimensional analysis to cancel things out, but what we need to use is the coefficients on a given equation. So you have to be able to balance equation. If the equation's already balanced, you're good, but each equation is going to have a different mole-to-mole ratio. So you have to look to the equation in itself in order to answer your question. Now, I'm not going to go to the doc cam here because it's already nicely worked out here. So if I were to ask you, how many moles of oxygen do I need to react with 2.4 moles of benzene? I start my equation with 2.4 moles of benzene. Now, looking at this chemical equation, it says for every 2 moles of benzene, you need 15 moles of oxygen. So I'm going to set this up so that moles of benzene on top is canceled by moles of benzene on bottom. Now, as I was saying, so, as I set this up, that we have 2.4 moles of benzene here. We have 2 moles of benzene there. Those two things would cancel out because we have one on top and one on bottom, one on the numerator, one on the denominator. The 15 moles of oxygen would be left. And so you get what? 2.4 divided by 2, which is 1.2. And then you get 1.2 times 15. So you could calculate 18 moles of oxygen would be consumed to burn all that benzene. You also could ask any question of the product. When I burn the benzene, how much carbon dioxide would be produced when I burn this benzene? So I can set up right here. For every 2.4 moles of benzene, you get a 2 to 12 ratio. Now you're going to see me as I work on the doc cam. I'm going to try to show the entire units. The units are what help guide me here. I may sometimes get lazy, but these units here are going to tell me why it's 12 over 2 and not 2 over 12. Why I'm not dividing by 6, but I'm going to multiply by 6. Because I want units of moles of benzene to cancel out with units of moles of benzene to give us the only units of moles of CO2 left. So the first thing we need to do is just to convert 1 mole to another. Where we will eventually take this, and we've jumped right in, is go from mass to mass. So how much, if I have so much benzene burning, how much water will be, what's the mass of water formed? We're going to turn, say, mass of reactant 1 into mass of reactant 2, or mass of reactant 1 into mass of product 2, or product 1. And so from this, we will always go through a mole-to-mole conversion. In order to go from mass to mass, we always have to go through moles. The reasoning behind this is that the weight, essentially the atomic density of every compound is different. If I just looked at the weight of carbon dioxide to carbon monoxide is 12 plus 16 or 28. Carbon dioxide would be 12 plus 32 or 44. So just comparing that, 28 versus 44, you're going to have, for every 1 mole of each of those, one is significantly heavier. So we can't just compare like a 1-to-1 ratio. If I'm going from carbon monoxide to carbon dioxide, if I'm oxidizing that, because one is heavier, one is you're gonna have to take on more weight. So for example, if I want to calculate how much water is formed from 78 grams of benzene, and in this case, I'm doing it in 3 steps. If you can set this up, you can do this in 1 step. You can set it up on one massive cross-hatch reaction, one massive like railroad track type setup. I'm doing it in these 3 steps just to break it down and make it a little bit simpler. But you could do it in 1 big step by combining step 1, step 2, step 3 all together, like you'll see down here. But to calculate the moles, first you'd have to calculate the moles of benzene. I set it up so that I have 1 mole of benzene. You would say 12 times 6 is what? 72. And then 1 times 6 is 6. 72 plus 6 is 78. So 78 grams of benzene is exactly 1 mole of benzene. Then I have our mole-to-mole ratio. For every 2 moles of benzene, I would get 6 moles of water. So you'd get, well, 78 grams of benzene would form 3 moles of water. Then finally, for every 3 moles of water, a mole of water weighs 18 grams. And so when I burn 78 grams of benzene, I would get 54 grams of water. Now, if I asked how much oxygen is needed to completely combust 14 grams of benzene, so I start my number with 14 grams of benzene, and I know I need to end with grams of oxygen. So in this case, I'm doing it all in 1 big step. Grams of benzene cancels out with grams of benzene. Moles of benzene cancels out with moles of benzene. Moles of oxygen cancels out with moles of oxygen, and I'm left with just grams of oxygen on top. So in this case, you would say 14 times 15 times 32, all that divided by 78 and 2. Please note that you don't accidentally multiply by 2. You would do 14 times 15 times 32 divided by 78 divided by 2. And that would give you 43 grams. So this is one of the big things we're going to have to be able to do. Almost every part of this chapter, there's a few more things we will introduce in this chapter, but almost everything in this chapter will come back to this basic process. When I talk about limiting reagents in a few minutes, maybe like Friday, if I don't get to it today, limiting reagents will require you to do this 2 times. When I calculate percent yield, you'll have to do this and then compare this to actual yield. You'll have to calculate mass to mass to calculate at what's called a theoretical yield and compare it to a number you actually observed in lab. So all these things will come back to this mass to mass conversion. We need to be able to do this. So please, please, please don't let this slack. Rather than jump straight into limiting reagents, I'm going to just create a practice problem whole cloth just to give us practice doing this. Let's say well, this is a common one. We've done this one before. Aluminum plus iron oxide goes to aluminum oxide and 2 iron. If I have 89 grams of aluminum, how much aluminum oxide? So that's what I want to, the question I want to ask. How much aluminum oxide could I form? Now, the thing we need to know is, so aluminum weighs 27 grams per mole. We can get that from the periodic table. And thus, aluminum oxide would be 27 times 2 and 16 times 3. So 27 times 2 plus 16 times 3. That would be 102 grams per mole. So with that in mind, I'm going to set this up. 89 grams of aluminum. I'm going to just put this over 1 just for the sake of showing that this is on the numerator, not a denominator. So the next step, I'm going to go grams to moles. So grams to moles to moles to grams. The stepwise path we're going to take. So with 27 grams, say 27 grams of aluminum per 1 mole of aluminum. Now, grams of aluminum only cancels with grams of aluminum. Grams of aluminum will not cancel with grams of aluminum oxide. So that's why I'm showing all the units. For every 2 moles of aluminum, we would get 1 mole of aluminum oxide. Once again, moles of aluminum only cancel with moles of aluminum, not moles of aluminum oxide. These are 2 different numbers. 2 different numbers. I cannot, they're not. Let's see if I can get that down a little bit better. And then finally, here's where I use my last number. For every 1 mole of aluminum oxide, this would weigh 102 grams of aluminum oxide. Moles of aluminum oxide cancel moles of aluminum oxide. So we get 89 divided by 27 divided by 2 times 102. You can do this in really any order as long as you keep order of operations in effect. You can put all the stuff in parentheses and all the stuff on bottom in parentheses, or I can just divide everything on bottom. Divided by 27, divided by 2. So how many grams of aluminum oxide would I form? 168.11. Because 2.2. because we are gaining a significant amount of mass from oxygen. That each aluminum weighs 27, but each oxygen weighs 16, and we're getting this in a 3-to-1 ratio. Let's see if we can get the light back on. Sorry. So 168.11 grams of aluminum oxide, gaining a significant mass in terms of oxygen. Okay, so that's just an example of what we need to be able to do. That's the big thing. That's the big thing. Everything else kind of goes from there. So one of the first major concepts, how this will be used, will deal with limiting reactants. That reactions don't always go to completion. They don't always react completely. So often left behind. In order to force the reaction to as much completion as we can achieve, oftentimes one compound will be put in excess. Usually it's going to be the cheapest. The other compound consumed. When the one compound is fully consumed, the reaction must then stop. Thus, we have the limiting reactant. A good example would be, so you start a campfire. To burn a campfire, you need two things. You need fuel source and you need oxygen. If you let it burn, what's going to probably go out first? When all the wood is consumed, the fire goes out on its own. Now let's take a candle, for example, instead. A candle, the fuel source is the wax. It's burning the hydrocarbons in the wax to make the CO2 and water and the pretty smells. If you've ever if you have one of those Yankee candles and you put the lid on it, it will rapidly put itself out. In that case, the wax is still remaining. The wax isn't burning, but the candle has put itself out. In this case, it has consumed all the oxygen available in the candle, and thus the oxygen becomes the limiting reactant. So whatever runs out first, the reaction is going to instantly stop. So by definition, when the reaction is done, the limiting reactant should be completely gone. And the reactant in excess should still remain. We're going to use a limiting reactant to determine how many products are formed. So whenever we're giving two different masses of two or more reactants, and how much of product A could be formed, we always must consider the limiting reactant as the factor, the limiting factor. So in this case, say I wanted to make hydrogen gas. Easily put magnesium strips into hydrochloric acid, and it's going to bubble out hydrogen gas. If I put this in there, I get this reaction. It starts bubbling. Eventually, you will get to one of two different situations. Either it stops bubbling and there's some magnesium left in the bottom. In this case, the amount of acid that was in that solution has been fully consumed. And so we can no longer go to products. In situation C here, it looks like all the magnesium was consumed. While we can't directly tell how much acid is left because it's a colorless solution, the fact that there is no magnesium left remaining undissolved kind of suggests that magnesium was the limiting reagent. Now, you could have a situation where they both get fully consumed, but more often than not, one will be consumed in the other will be remaining. So now this is actually the method they teach in the book. I went ahead and copied it from the book. Honestly, I'm not the biggest fan of this method. So there's, no matter what you do, limiting reactant, unless you're just an amazing guesser, a limiting reactant problem is a mass to mass conversion that you have to do twice. Now, the way the book suggests is that you convert the mass of a reactant A into the mass of reactant B, and then thus comparing how much reactant A would react with reactant B. Saying like, okay, no, I actually say, yeah, I actually changed it. Thank God. The book would have you then compare the two reactants and then figure out which one is limiting and then convert it to products. The way I like to do it, and the way I have it on the slide, is I'm going to convert reactant A to the product. Then I'm going to convert reactant B to the product. And I'm going to count a product that could be formed from A and the amount of product that could be formed from B. So depending on how much is going on, if the amount of product that can be formed from A is greater than the amount of product that can be formed from B, you take the B as limiting. If the amount from A is less than the amount from B, then A is limiting. So the two numbers, if I'm calculating product from A and product from B, the lower one comes from the limiting reactant. The lower one is also the one that would run out first, and the lower one would also be the end result. So no matter what, you have to do this mass conversion twice unless you have sometimes a 50-50 shot. Now, if you're cavalier like that and you're going to just do it once and make your guess, then fine. But unless if you're trying to actually know the correct answer with some certainty, you have to do this mass-to-mass conversion twice. Now, for the sake of this, I've used molecules, but looking at this, if there's 16 molecules of, this is methanol, 25 molecules of oxygen, which will run out first. So if I'm going to calculate this in terms of CO. 25 molecules of oxygen. For every 3 molecules of oxygen used, we form 2 molecules of CO2. So 25 divided by 3 times 2 is 16.67. So if I use up all the oxygen, I would get 16 2/3 of a molecule of CO2. Ignore the fact that you can't really have 2/3 of an atom. If I had 16 molecules of methanol, for every 2 moles of methanol, we molecules of CO2. In this case, you'd get only 16 molecules of CO2. So if the oxygen is fully used up, I get 16 2/3. If the carbon dioxide is fully used up, I get 16. So methanol will result in less product. The methanol will limit the scope of this reaction, and the methanol controls how much product can be formed. So it's the methanol that has the controlling factor. There's less of it to go around, so it has the controlling point. It's our pivot point for this reaction. Now, we can use the same method when using moles of reactants and grams of reactants. Once we have the limiting reactant, we can know how much product is formed. So iron oxidation. Iron oxidation. We oxidize iron oxide. If I have 16.7 moles of iron and 12.2 moles of oxygen, what is the limiting reactant? And how many moles of iron oxide could be formed? Anytime you have a problem where you have two masses of reactants, you must think limiting reagent. If I just say I have 16.7 moles of iron with excess oxygen, then we only have to do it once. But anytime I give you both, it's oftentimes a limiting reagent problem. So in this case, from moles, 16.7 moles of iron would have, for every full mole of iron, we have 2 moles of iron oxide. Using those numbers, you would get 8.35 moles of iron oxide. Now, even though, yeah, this one is kind of a little bit more obvious, but sometimes the heavier number can still be the limiting reagent depending on the mass of each guy. 12.2, we use the 3, we use the 2. So for every 3 moles of oxygen, we form 2 moles of iron oxide, form 8.13 moles of iron oxide. So which one of these numbers is lower? 8.13. So what is the limiting reagent? Oxygen, because we converted oxygen into iron oxide. How many moles of iron oxide could be formed? 8.13. Looking at copper, then goes to CuO. Now this may be a little counterintuitive. For every 85 grams of copper and I have 27 grams of oxygen, what is the limiting reagent? You may be wanting to say, well, 85 grams is much heavier than 27 grams, so clearly it's going to be oxygen. But you got to remember, copper is far heavier than oxygen. And you'll need 2 moles of copper versus 1 mole of oxygen. So in this case, I convert grams of oxygen into moles of oxygen. 1 mole per 32 grams. For every 1 mole of oxygen, those two cancel. I'd get 2 moles of copper oxide. And copper, which is like 63.55 grams, making the molar mass 79.55. For every 1 mole of copper oxide, we would get 79.55. So 27 oxygen is responsible for about 130 grams of copper oxide. However, 85 grams divided by 63.55. There's a 2-to-2 ratio. And when we convert this into from moles back to grams, you get only 110 grams of copper oxide. So even though there's a greater mass of copper, copper is the limiting reagent. And so how much copper oxide could be formed? You would choose mass like 110. Now, writing this out, 2Fe2O3 plus 6 carbon and 3 oxygen goes to 4 iron. This is essentially what occurs within a blast furnace. We throw charcoal and oxygen and iron ore in there, and what we're doing is we're converting the iron ore back into iron that we can pour into make steel. The carbon gets oxidized to CO2, the iron gets reduced. While oxygen is definitely in excess, we have 144 grams of coal, and we have about 480 grams of iron oxide. So What is the maximum amount of pure iron that could be produced with this mixture? So I'm going to go to the dot cam. Okay. So the first thing we need to note is, what is the molar mass of carbon? Carbon is 12 grams per 1 mole. If you want to get really nitpicky, iron is about 55.85. But for our sake, for the sake of this math, I'm going to say it's approximately 56. So Fe2O3 Fe2O3 is 56 times 2, and it's plus 16 times 3. If I remember right, it's 160. Yeah, it's 160 grams per mole. 160 grams per mole. So I'm going to turn carbon into grams, and then I'm going to turn iron oxide to grams of iron. So I'm setting this up 144 grams of carbon. Now I have to divide by 12 grams of carbon per 1 mole of carbon. Of carbon from here for every 4 moles of iron, and 1 mole of iron is 56 grams of iron. That's grams of carbon. Moles of carbon, moles of carbon, moles of iron, moles of iron. Notice all the units in the one I'm looking for at the end. We have to be able to set this up so the last unit is the one we want to keep. That is a big skill for almost all the math, that the units you have tells us how we set this up. So 144, I'm going to say divide by 12 times 4 divided by 6 times 56. So how much iron could I form from carbon? It's 448 grams of iron from my carbon. Now, if I have 480 grams of iron oxide, how much iron could I form? As we said, we had 160 grams of iron oxide per 1 mole of iron oxide. Now, as I said, sometimes I might get lazy and just say mole. But this putting the mole of iron oxide is going to tell us, is this go on bottom or does that go on top? Does the mole of iron go on? I'm trying to show all of the units in order to help keep track where these all go. So grams of iron oxide, moles of iron oxide, moles of iron. We're just left the units of grams of iron. Now, so I start with my 480. Divide by my 160 times 4 times 56. And this would get 336 grams from the iron oxide. Now, if we're trying to make iron, this makes perfect sense. Why this limiting reagent? I have no more iron I could form. I've run out of my iron ore. Keep the furnace all you want. I can't more iron. Now, if you run out of carbon, it's maybe a little bit less clear. But what happens when you run out of carbon? You run out of carbon, essentially the furnace goes out. If the furnace goes out, stops burning, metal cools down, you're not going to convert it back. You're just going to have iron waiting for more charcoal to be put in. In this case, I run out of iron ore. I've melted all the iron I can. I can't extract any more out. So this is a case of I just to moles, to moles, to grams. And I just do it twice, and I look at which answer is the right one, which answer is the lower one. And that is going to be our limiting reagent. We're going to go ahead and stop there. But next slide, we go into percent yield. Percent yield, which is essentially more of the same, except maybe almost a little bit easier than limiting reagent, but it's a lot of the mass to mass conversion, just applied in a different way. Thank you for your time, and I will see you guys Thursday-ish, the test.